So good evening and welcome to Public Observatory Night presented by the Center for Astrophysics, Harvard and Smithsonian. My name is Nadia Whitehead and I'm a Public Affairs Officer here at the Center for Astrophysics. I'm excited to present tonight's lecture, Monitoring Air Pollution from Space in a Virtual Format. We're streaming to both Facebook and YouTube. We'll have time for questions at the end of the presentation, but if you have a comment or question during the presentation, just type it into the comments section of Facebook or YouTube. We'll get to as many as possible at the end of the event. If you're interested in receiving our e-newsletter and information about future observatory nights and other events, please make sure to sign up for our mailing list by visiting the link that's going to be appearing on your screen now. All right, I'm excited to present tonight's guest presenter, Caroline Nowlan, who will be introducing us to the TEMPO instrument. Scientists at the Center for Astrophysics have been working on the TEMPO project for over 10 years, and it's finally scheduled to launch next month. So we're very excited to share the project with the public today. Now, here's a little bit more about tonight's presenter. Caroline Nowlan is a physicist in the Atomic and Molecular Physics Division at the Center for Astrophysics, where she works on remote sensing of the Earth's atmosphere using satellite and aircraft instruments. She is a member of the team working on NASA's Next Generation Air Quality Satellite mission, TEMPO, and is an investigator on projects examining urban air pollution in the US and Korea using remote sensing of the atmosphere from aircraft. Caroline earned a bachelor's in physics from Mount Allison University and a master's and doctoral degree in atmospheric physics from the University of Toronto. She completed a postdoctoral fellowship at the University of Toronto, as well as here at the Center for Astrophysics, Harvard and Smithsonian. Please join me in welcoming Caroline. Caroline, I know you've had a super busy week, so we really appreciate you sharing about an hour of your time with us today. I'm going to let you take it away and start your presentation.
Okay, great. Thanks a lot, Nadia. Well, it's great to be here tonight doing one of these talks. The last time I was at one, I think, was 2019, giving an introduction, but that was actually in person. So this evening, I'll be talking about monitoring air pollution from space. So the first half of my talk is going to be pretty general about how we do this, a little bit of history, and the sort of techniques we use. The second half, I'll be talking about a new instrument called TEMPO. And the reason I'm giving this talk now is because TEMPO is about to launch. So it's going into space in April next month. So these are exciting times. All right, so my presentation has some contributions from a few colleagues who are listed on the left, but some of the people from the TEMPO science team are in the right, on the right-hand picture. This is just a few people who've worked to make TEMPO a reality. So in fact, there's probably upwards of maybe 300 or 500 people who've worked in or contributed to TEMPO in some way, from different federal, local, and state air quality agencies, from universities, from industry, and from Mexico, the United States, Canada, and further afield. So before we get into all the technical details, just think for a minute about what's in the air you breathe. And maybe this is something you haven't thought about before if you're lucky to live in a really clean area, or maybe if you live in a more polluted area, that might be something that you think about quite a lot. Hopefully by the end of this talk, I'll be able to share some information so that you can understand a bit better what you're breathing every day. So why does air quality matter? And I think intuitively, most people know that air quality matters, but I'm going to get into some of the details here. And I've just divided this into three general topics to go through. So the first one is health, so human health. Now, poor air quality leads to premature mortality and chronic disease. In the United States alone, about 70,000 people are estimated to die every year prematurely from poor air quality. This is actually down in the last 10 years. Previously, say 10 years ago, it was more like 100,000. But air quality in the US is actually generally often getting better. And so premature mortality has decreased somewhat. Globally, it's an even bigger problem. About 4.2 million people are estimated to die prematurely every year around the globe. That's from outdoor air quality alone. So indoor air quality contributes several million more. Recently, this is the last estimate from the World Health Organization, but some recent studies, I think, have indicated this number could be even higher. And poor air quality increases the risk of various problems, including asthma, respiratory diseases like COPD, lung cancer. Those are maybe some more obvious ones because you're breathing in this poor air. But poor air quality is also linked to things that you might not think of initially, like preterm birth. Maybe up to 5% of preterm births, I believe, in some parts of the US are probably due to poor air quality. And things like heart disease, stroke, diabetes. It's also been linked with several other things like dementia. The strongest links for premature mortality, at least, are with fine particulate matter. So that's, or we often call it PM 2.5. That's particulate matter that's less than 2.5 microns in diameter. And those are particles that are suspended in the air. So not gases, but solids suspended in the air. Also with ozone, nitrogen dioxide, and sulfur dioxide. Second, I'll talk a bit about poor air quality in ecosystems. So poor air quality or nitrogen that's released from combustion can lead to eutrophication. That's a long word that I didn't even know what it meant until I started studying this. But nitrogen is a nutrient. So plants and algae love nitrogen, and you give them more nitrogen and they will grow more. Unfortunately, some plants grow better than others, and this can lead to a loss of biodiversity, or in the case of algae, it can lead to blooms. Most inland water bodies, it's from more like fertilizer runoff and that kind of issue, but in coastal areas in particular, air pollution can contribute a significant amount of nitrogen to water. Acidification is another problem. When I was younger in school, acid rain was what we talked about a lot in our science classes. And if you have sulfur and nitrogen in the air, it has to go somewhere eventually, and it can be rained out. Or if it's in a gas form, it can stick to a surface and be absorbed, and that can acidify soil and water. As well, we can have ozone damage to vegetation. So ozone doesn't just damage people's lungs, it also damages vegetation and crops. And this can have significant impacts when it affects crop yields or forestry yields. And ozone is something that most people have heard of, but I should start off by saying that ozone up high is good. It's a good thing. So ozone in the ozone layer way above us, that protects us from UV radiation and allows life to thrive on Earth. But when you have ozone at the ground, it's an air pollutant, and that's not good. The third is climate. So climate and air quality are really intimately linked, and it's hard to kind of separate them. Even in my own field, we sort of do talk about them in two bins sometimes, but there's a lot of feedback between both of them through atmospheric chemistry and other ways. So first of all, the nitrogen oxides that are produced typically through combustion can react with volatile organic compounds in the atmosphere and produce ozone. So we already mentioned ozone, but ozone is important for climate because it's also a greenhouse gas when it's down low. Nitrogen oxides and volatile organic compounds can also form what we call secondary organic aerosols. So those are not things that are directly, aerosols are particles that aren't directly produced, but they're produced from the reaction of these gases. And if you have aerosols in the atmosphere, those can actually reflect light back to space. And so it can have a cooling effect on the climate. Then we can have feedbacks on air quality from climate change. So if the Earth is, or if somewhere is getting hotter, you can get more smog produced. If it's getting drier, you can get more wildfires, which then makes air quality poorer, and also particle pollution from, say, dust. And there's many more interactions through atmospheric chemistry where different pollutants can change the chemistry of the atmosphere. And cloud formation, clouds form on these aerosols. So if you have more clouds, it's reflecting more light back to space. Plant growth, again, they absorb nitrogen. They also want carbon. So it can, nitrogen can perturb how much carbon the plant can take up as well. Now, how do we make these measurements? So this is a map of surface monitors of ozone from the EPA, the Environmental Protection Agency, and you can go to their website and look at this data for any day. So this is one day in July of last year, and you'll see the red and orange, those are high levels of ozone. Yellow is kind of moderate ozone, and green is clean. But one thing to note is that there are a lot of monitors in the United States, but they're not necessarily in every location. So you go to some states and maybe you only have like 2 or 3 monitors. Typically, the urban areas are monitored a little more heavily. And you go to a place like Mexico, where it has a lot of polluted cities, and there's not a lot showing up here. And ozone is actually pretty heavily monitored. Some of the other molecules that we look at, like sulfur dioxide and nitrogen dioxide, there's even fewer monitors. And something like nitrogen dioxide, it's emitted, it only has a lifetime of about maybe a few hours. And so it can't travel very far away from its source. And if you have a power plant that's emitting this pollutant, but your monitor, the wind is blowing it in one direction and your monitor is on the other side, it can't accurately measure what's going on with that power plant. So one way, there's many ways to measure the atmosphere through ground-based monitoring or aircraft or balloons. But one way that we measure is with satellite remote sensing. And that's what I'm going to be talking about today. So satellites are really useful because they can provide continuous mapping of the whole globe and remote monitoring. So we can measure pollution over the Arctic. We can measure it over the oceans. We don't need to have a surface monitor there, as long as there's no clouds anyway. There's currently 8 instruments in what we call low Earth orbit. So these instruments are, and these come from various US agencies, NASA, NOAA, the European Space Agency, China has one up right now. And these instruments are what we call low Earth orbits. So these orbits are about 700 kilometers above the surface of the Earth. And the instrument is orbiting the Earth about 14 to 15 times a day. And it's going over the same location on Earth at the same time every day. And so we can measure the amount of a pollutant over a particular city at, say, like 1:30 in the afternoon. So we can, over years, look at trends of this city at 1:30 in the afternoon, and we can understand it in the context of other places in the world. But there's a lot happening in air pollution over a day. And right now, we can't see the cycles of air pollution over a whole day. This is about to change. So in the TEMPO instrument, which is being run from the Smithsonian Astrophysical Observatory where I work, is going to be able to make these measurements every hour over North America. So I'm going to get into TEMPO a bit later, the details of TEMPO, but right now I'm going to talk about how we do the measurements. So TEMPO is exciting because it's launching next month. This is very timely. So first, let's look at some of these low Earth orbiter measurements. And if you've seen a map of the ozone hole that looks like this, then you've seen data from these low Earth orbiters. So for a couple of decades now, the low Earth orbiters that we use to measure pollution are also measuring the ozone hole. So here's a map of the ozone hole over Antarctica from a single day in 2014. And blue is the low ozone, and green is higher ozone. And so these instruments are used regularly to map the ozone hole. They've also been in the news quite a bit lately because they've been used recently to look at pollution reductions from the COVID-19 lockdowns in 2020. So there's been a lot of scientific studies about this recently. And this is a instrument called OMI for short, or Ozone Monitoring Instrument, and it's a joint NASA Dutch instrument, which has been flying in space for almost 20 years now. And here is some data of nitrogen dioxide over the northeastern United States in March, averaged from 2015 to 2019. And so you can see the really dark areas are nitrogen dioxide, or NO2, over New York City. In my own region of Massachusetts, it's more red, Boston. But this is you can take this average data and look at nitrogen dioxide over this region. And then in the next slide, we move to March 2020, and you see massive reductions. And this is primarily because nitrogen dioxide is mostly produced by combustion of fossil fuels. And so people stopped driving so much, and there was a huge reduction in NO2. And this was seen in many countries around the world. So just go back again, that's 2015 to 2019 average, and then the difference in 2020. It's since gone back up, as you might imagine. Okay, so how do we do these measurements? So here's just a cartoon showing the geometry that we use. So this is called nadir backscatter. We're looking at ultraviolet and visible light. So light comes from the sun and it's reflected off the surface of the Earth or off clouds back to the satellite. And so we can see, you see there's the white ring around the Earth represents the atmosphere. And so there's a path that the sunlight is going through on its way back to the satellite. And we look at what sunlight is absorbed by the atmosphere. Oops. The way we do this is using a spectrometer. So on the right-hand photo here, this is the insides of the tempo, or part of the inside of the tempo instrument. And you'll note the different colors. So what happens is that we take that sunlight and we use a spectrometer to basically break it into different colors or different wavelengths of light. And the lower left-hand plot, this is a kind of more technical plot, but I know a lot of people who watch these Observatory Night talks have a technical background and might be kind of interested in this stuff. So I'll go through it, hopefully slowly. So here I have a plot of reflectance versus wavelength. So wavelength is the color of the light, and we go from about 300 here nanometers to 800. And this is real data from a satellite instrument called GOME that was flying about 20 years ago. And these are just 4 measurements. So the reflectance of 0 means that no light is reflected back. So that's like total absorption. And a reflectance of 1 means that all the light is reflected back. So if you look at, say, the red one, this is from a fully cloudy scene. And if we just look at the broad features here, we see that it's about a reflectance of about 0.8. And that is because a cloud is white. It's reflecting almost all the colors back to space, almost equally, except in the ultraviolet, where there's really intense ozone absorption. And if we look at the broad features of the other ones, say the Sahara Desert, that's the brown one, it's reflecting more back at the longer wavelengths. Those are red wavelengths, and that's what wavelengths. That's why the Sahara looks red. And then if you look at vegetation in green, you see this sharp feature around 700 nanometers. That's called the red edge. That's where chlorophyll stops absorbing visible light. And that's actually used to measure vegetation indices from remote sensing. The blue is an ocean. An ocean is dark, so it's not reflecting a lot of total light back. And it's not reflecting light at longer wavelengths like red light. But what we actually are using to make these measurements of gases are these fine features. So if you look at the red line, you'll see lots of squiggly lines in there, not just a broad spectrum. And these are from absorption by different gases. So there's a lot of really strong absorption by oxygen and water vapor in these regions. And some of the trace gases that we measure, though, they have much smaller absorption, but we can fit modeled spectra, excuse me, to the measured spectra to derive the amounts of trace gases. So what can we measure? Excuse me one sec. Now, we can only measure gases that first absorb in the spectral region, and secondly, there has to be enough of it. So we can measure ozone, nitrogen dioxide, sulfur dioxide, and aerosols. And those are, excuse me, those are really important because they make up 4 of the 6 EPA criteria pollutants. The others are carbon monoxide and lead. You can actually measure carbon monoxide from space as well, but not with the kind of instruments that we use. The second ones are formaldehyde and glyoxal. These are volatile organic compounds. And formaldehyde is really useful because it's actually produced when other volatile organic compounds, then there are thousands of them, break down in the atmosphere. So we can use it to infer the emissions of other volatile organic compounds. The other ones in blue are bromine monoxide, iodine oxide, and chlorine monoxide. And these are actually not really as important to air quality, but they're involved in ozone chemistry. Water vapor is another thing we can measure, and that's important for weather and climate. And then oxygen, that's not really important for air quality, but it's actually really useful because we can use it to determine if we have clouds in the field of view. So where do these come from? I've talked a bit about all of these already. Nitrogen dioxide primarily comes from burning fossil fuel. There's also big sources from biomass burning. So that can be human-caused biomass burning, like agricultural fires, or it can be from wildfires. There's also some smaller sources from natural sources from lightning and from soil emissions. Formaldehyde, as I mentioned before, is produced by other volatile organic compounds when they break down in the atmosphere. And it can also come from industrial processes and biomass burning. In the United States, the biggest source of formaldehyde is actually natural vegetation. So heat-stressed forests, particularly in the summer, make something called a VOC called isoprene, and that eventually degrades to formaldehyde. And ozone is actually not produced directly. So ozone is produced when nitrogen oxides and volatile organic compounds react in sunlight. So it's a secondary pollutant. It doesn't have primary production. There is a natural source of ozone that occasionally you can get in some locations, like high altitude locations like Colorado, where ozone actually comes down from higher altitudes in what we call a stratospheric intrusion, where the ozone comes down to the surface at high altitudes. So now let's get on to TEMPO and how TEMPO is going to contribute to our knowledge of air quality. So TEMPO stands for Tropospheric Emissions, Monitoring of Pollution. And it's going to be making, as I mentioned, hourly daylight observations. So we can't measure at night. We need to have the sun to do these observations. Its spatial resolution is about 2 by 4.75 square kilometers. And it's going to be on an Intelsat satellite. And Intelsat is providing satellite internet. So if you're on an airplane, you might be using Intelsat internet. And this is interesting because TEMPO is going to be, NASA doesn't usually launch on commercial satellites. In fact, I think TEMPO might be the first or second satellite instrument, NASA instrument to go on a commercial satellite. So this is a very new thing. It's not going on a NASA satellite. And the launch, again, I mentioned is next month. The first measurements we're going to get are in about 6 months. So there's a lot of sort of turning the spacecraft on, turning TEMPO on, et cetera, before we actually take an observation of the ground. And then we have about 6 months where the team will be evaluating the data and comparing it with ground-based observations. And then hopefully the data will go public in the spring of 2024. And on the right-hand side is an image of TEMPO being integrated with the spacecraft. So TEMPO is the shiny silver box on the very top, and the spacecraft is below. And I don't know if you can see, but way in the background, there's a small person. So TEMPO is about 1.5 meters by 1 meter, to give you some scale. And the principal investigator of TEMPO is Kelly Chance. If you ever attended these observatory nights in person, Kelly gave a talk on TEMPO about 3.5 years ago. So you might recognize him. TEMPO is a collaboration of several institutions across the country for running the instrument and building the instrument. So the science data processing and the instrument operations are happening at our own institute in Cambridge, Massachusetts. It's on an Intelsat satellite, and Intelsat will be operating the satellite itself. The science data archiving and the project management has been taking place at NASA Langley in Virginia. The instrument itself was built by Ball Aerospace in Boulder, Colorado, and Maxar Technologies built the spacecraft for Intelsat. Now, the reason that TEMPO can do these measurements is because it's being put into geostationary, these hourly measurements is that it's being put into geostationary orbit. So the technology in a way and the retrieval, the algorithms are they have a long heritage, but the orbit is really the game changer. So we have made these measurements from low Earth orbit before, but now when you put this instrument into geostationary orbit, it's essentially sitting over the equator and can look at North America all the time. So a geostationary orbit is much, much farther away from the surface of the Earth than a low Earth orbit. And if you put the satellite into an orbit at 35,786 kilometers at the equator, it will orbit the planet with the same period that the Earth rotates. So the Earth rotates in 24 hours, and the satellite goes around the planet in 24 hours. So it's essentially sitting at the same location. And this is a really common orbit for weather satellites and communication satellites, but it hasn't been used before over North America for an air pollution gas monitoring instrument. So you can see this, if you've seen these nice pictures of hurricanes moving every minute with really high resolution, those are typically taken from a geostationary weather satellite. All right, and now there's a movie that, here we go. So here is the Intelsat satellite with TEMPO on the very end. And so we're going to be doing these scans of North America every hour. So from the Atlantic to the Pacific every hour. And the field of what we call the field of regard is from just south of Mexico City all the way up to the Canadian oil sands. So we'll be also covering Puerto Rico. I don't think it's shown actually in this plot, in Cuba as well, as most of populated Canada and the continent or the contiguous United States. We don't see Alaska though, unfortunately. All right, and the next slide here. So again, this is a bit of a busy slide, but I think it's important and interesting to kind of understand what pollution can look like in a day and the advances that tempo can help us make. So this is a slide showing NO2 pollution over Houston on 2 days in 2005. So the top two colorful panels on the center and right top panels show OMI NO2 column on June 22nd and June 23rd. So these were overpasses of actual satellite data that were collected over Houston. And the left top panel is showing model simulations from the CMAQ model. It's an air quality model. And let's now look at the line plot. Excuse me. So the column, you can ignore the kind of pink one that says CMAQ surface NO2. So these satellite instruments can't really measure the exact surface pollution. What we see is a total column of air. And that can be tied with our knowledge of the surface through models, and that's actually a fairly complicated process. But we basically are looking at a column of pollution. So what's happening to the NO2 over 2 days? It's changing a lot. So if we look at just the yellow blocks, that's when the sun's up. So that's daytime. That's what tempo is going to see. So you can see on the first day that blue or dark purple line goes up, up, up during rush hour, then it drops, and then it rises later in the day. And then overnight, there's a little bit of change. And then in the next day, it rises again during rush hour, drops, comes back up. Now, the large red dots are what we see with the OMI satellite instrument. So that's what we see from low Earth orbit. And you can see we've got 1 point on each day, which is great that we have that measurement, except that we can't see the changes over the day. And so what tempo is going to be able to do is actually measure that change, that every hour, that pollution, and we'll be able to look at the cycles of pollution over a day. And with OMI, not only are we only seeing once a day, we're actually also annoyingly seeing when the pollution is at its lowest level. So we're not getting a full picture of what's going on in Houston. But tempo is going to be able to change that. So the great thing about tempo is we're also really getting down to really high spatial resolution. And so if we look at these blue and orange boxes, these are currently the ground footprints of a pollution measurement from a couple of instruments that are in low Earth orbit right now. GOM-2 is a European instrument on their weather satellites. There's 2 of them in space right now. And OMI is this, again, the one I showed with the COVID-19 lockdowns. And tempo is in red. So you can see that there's a really big improvement in spatial resolution. This is the Washington, D.C. area. So before, OMI was seeing something of the size of the entire city of Washington, D.C., but tempo is getting down to like a suburban scale now. So we'll be able to see much better what's happening on a much finer level. There is one low Earth orbiting European instrument that has a resolution that's almost as good as tempo, called Tropospheric Emissions. But tempo, again, is going to provide that hourly data in addition to this high resolution. Now, tempo is expected to be used for many applications, and there's a whole program that's being run out of NASA Huntsville in Alabama for bringing in users. And so this is like they are providing simulated tempo data to various air quality agencies, to local health air quality managers, to epidemiologists who are then learning how to use the tempo data and how it can help them in some of their studies or emissions estimation, all kinds of things. So these are just a few of the fields that our tempo data is expected to be used in. So the first is public health. Again, people are interested in looking at chronic exposure to different pollutants, but as well as extreme exposure. So if you have like really high ozone levels on one day, does this influence, say, the number of people being treated for asthma in the emergency room? Regulatory science is another one. So a lot of agencies are interested in is the pollution. If our city is seeing a lot of pollution, is that pollution that we are producing ourselves, or is that pollution that's coming from out of state, perhaps? Or in the case of someplace like Denver, is this ozone locally produced ozone, or is this ozone that's coming from higher in the atmosphere? So Tempo can help to people understand pollution transport and different sources. And air pollution emissions and monitoring, this is something that the low Earth orbit data has been used for a lot. People have built databases of like the 500 most polluting coal power plants in the world, things like that, and estimating the emissions that are coming from those plants. That's actually really useful in some areas because there are in the United States, power plants have to report their emissions, but that's not always the case in every country. And air quality modeling and forecasting is something I think is going to really benefit from Tempo. So there's a lot of air quality forecasting that happens now that is not incorporating satellite data. And Tempo is going to be able to provide a lot of data and at all times of day. And so that's something that air quality forecasters are working on now, is how to incorporate this kind of data into a model. There's some links between air quality and weather. So if you have, say, like lots of aerosols in the atmosphere, this can lead to cloud formation. So that's also one area of impact. As well, vegetation and ocean monitoring, and this is kind of a funny one that you wouldn't think of necessarily with air quality, but from some of this data, it's not a main science product, but we can get information on vegetation indices, and so it's also and vegetation productivity, and so that's something else that people are interested in using Tempo for. Now, this is a case study that uses the Tempo Airborne Simulator to look at inequities and NO2 pollution over a city. So, excuse me. So a few years ago, NASA and Ball Aerospace both developed airborne instruments in support of Tempo. And these are instruments that are very similar to Tempo in design, and they put them on airplanes and they look down at the ground, and instead of scanning across the continent of North America, they fly the instruments over a city or over a power plant or whatever. And so this is an example of the results of one of the flights. And there's been lots of them now over various US cities. And the instruments they've been really useful because they've helped us develop algorithms to analyze Tempo data. And they're also now going to be used as what we call validation instruments. So they'll be flown under Tempo when it's in space to make sure we're measuring the same thing. But here's an application of some of that data. So it's a little bit of a busy slide, but the top left figure says GCAS NO2 VCD. GCAS is the name of one of the instruments, and this is the vertical column density over Houston. And so the instrument was flown over Houston on several flights over 2 weeks, and NO2 was retrieved using the Tempo algorithms that we're going to use. And so this was the kind of raw data of NO2. On the top right-hand panel, this is work done by our colleagues at the University of Virginia. They took that data and they put it onto block group census tracts to see how much NO2 is in each of these census block groups. Then they correlated it with the average per capita income. This is all from census data. Average per capita income, and also the highest block group level race, ethnicity demographic, again from the census. And they have a lot of other details in the paper, but overall, for example, they show that over Houston, at least on the days of these flights, low-income non-white neighborhoods see about 40% more NO2 than high-income white neighborhoods. And the same results have showed up in other cities that have been looked at, including New York and Denver. And the same group and some others are also using the same kind of techniques now to look using satellite data. But the low Earth orbiters. And when Tempo comes, it's going to give a lot more detail about how NO2, for example, is changing in a city over a whole day. And so these kind of studies will be really enhanced by that information. Another thing that we can do with Tempo is experimental opportunities. And so Tempo is going to be sitting in space and scanning the continent every hour and making a map of pollution, of formaldehyde, NO2, and ozone, and probably a few other things that we can measure, like sulfur dioxide and aerosols. But about 25% of the time is we allow for experiments that scientists can propose, or we can go and look at extreme events. So if a volcano erupts, we can actually use the instrument to quickly scan that area of the volcano with a 5 to 10 minute cadence. Or if there's a wildfire, we can go and look at that. Or an industrial accident, or if there's some kind of experiment that people want to do, like if they're flying a plane over New York City or something, we can go and look at New York City with really high time frequency. Now, TEMPO's not up there alone. There's actually two other instruments that form what we call the global constellation. The European Space Agency is going to be launching Sentinel-4 in the 2024 timeframe. And it's a similar instrument to TEMPO, making similar measurements. And the South Koreans launched an instrument called GEMS 3 years ago, and it's making measurements from Japan to India. And GEMS data has just recently become available, so this is an exciting time. This is some preliminary GEMS data, and this shows what the kind of stuff we expect to see from TEMPO. This though is South Korea, so that's South Korea and North Korea in the middle, and then China on the left-hand side. And you can, if you were to zoom in on this, you can see like individual sources like power plants, and of course, really polluted cities like Seoul. Now, a great thing about TEMPO data is it's all going to be publicly available. So anybody will be able to go to the NASA data archive and download all the data that they want. I should warn you though, there's over 1 terabyte a day. So you probably don't want to download an entire data set, but NASA will be having ways to download much smaller amounts of data for people who are interested. Now, I work for the Smithsonian, and a core part of that mission is public engagement. And there's a lot of work going on at the Center for Astrophysics in this field. So this is some work that my colleague Erica Wright is working on, and she's leading a project called BEST AQI. And so BEST AQI stands for, now I wrote this down, I always forget it. It is Breathing Easier, Supporting Teen Air Quality Investigations. And so she's leading an effort to engage museums and nonprofits across the country to develop programs for teen investigations into air quality. And so hopefully teens and youth will have access through these programs to instruments, data like TEMPO, and the analysis tools that will help them to pursue their own air quality investigations. So in the photos, we see a couple people who've, I think the top student who, the top photo shows a student who worked with Erica a couple of years ago. Also seen here are some low-cost sensors. So these are low-cost air quality sensors that could be accessible for students to use. And then through this program, also youth should gain the support that they can, for them to advocate for environmental action in their own communities. Another thing that the Center for Astrophysics and TEMPO team have been involved in are ozone bioindicator gardens. So these ozone gardens have been planted at museums and universities all over the country. And they involve planting different species of plants. So sometimes varieties that are say, resistant to ozone damage, and some that are not resistant to ozone damage. And people can go and look. We have one here. You can go and look and see at how the ozone has damaged the plants, say, over a summer. There's a link, I think, that might be in the provided in the comments to go and learn more about ozone gardens. And these two projects span the whole country. So in the blue points here are museums that are interested in implementing some of the best AQI investigation programs. And the green leaves show the location of different ozone gardens across the US. So again, let's come back to the original question of what's in the air you breathe. Hopefully after this talk, you have a better idea if you haven't thought too much about it before. And I think that satellite data can really add a lot of information for us to understand what's going on. And not only for individuals and communities, but also for regulatory agencies and state and local air quality agencies to better inform their jobs, and also for policymakers to better inform policy. I think tempo is really going to add a whole lot of detail and information, and we'll be able to see things that we've never seen before, and probably there's going to be lots of things that we didn't even know we didn't understand. But it's I think a really exciting time for measuring air quality. All right, thanks. And with that, I think I'll be taking questions now.
Yes, thank you, Caroline. That was a great presentation. I learned a lot about tempo, even though I already know a little bit about tempo. So everyone watching, it's now time to ask questions for Caroline. So if you have a question, just write it into the comments of YouTube or Facebook, and we'll pull your question up. I did see one question come in already. Let me get to that. So Brian on Facebook wants to know, will tempo be able to see the range of toxic fires, or how far or where the wind takes polluted air?
Yeah, definitely. We can, from the low Earth orbiting instruments that we use now, we can see a lot of fires. And we kind of miss things though, right? Because you see fires over, say, Alberta on one day, and then we don't see anything for another 24 hours. And by that point, it's traveled quite a distance. But even with the current technology we have, we can track the gases in these fires. There's actually instruments right in space and geostationary orbit that can look at aerosols from fires already. They're just not seeing the kind of toxic gases that we have, that we specialize in. But yeah, definitely we'll be able to measure that. And people are really interested in using this data to look at fires. So some of the sort of high frequency observation experiments that we will do will be when there's a big fire. We'll probably be able to measure them like every 5-10 minutes. And I think the next frontier is putting that into forecasts. So actually forecasting, where the plume will go.
Very interesting. Well, thanks for your question, Brian. So actually, I have my own question, follow-up question to that. So when a sudden event or a disaster happens like that, like a fire or a volcanic eruption, how easy will it be for tempo to kind of change course and hone in on that? Is it as easy as grabbing the joystick and just turning the instrument, or can you kind of walk us through that?
Yeah, I have to admit that's not my specialty, the instrument operations, but I think it depends on staffing, actually. So if someone is around and they can, it should be, I think, probably a matter of hours in some circumstances. If it's not like a real emergency, then maybe a day, 24 hours or something like that. It's probably the turnaround time. There is a procedure for doing this that, you have to test out commands and that kind of thing. So,
okay. Yeah. Thank you. All right. So I see a few more questions rolling in. So let me go ahead and pull them up. All right. Bennett on YouTube wants to know, with the satellite data, can we figure out the height of chemicals? Ozone on the surface versus high in the atmosphere in the column of air?
Yeah, that's actually that's a really excellent question. So it depends on what we're looking at. So formaldehyde and nitrogen dioxide, we're seeing a total column of it. And that's actually, for something like formaldehyde, that's not a big deal. Formaldehyde is basically near the surface, and there is no formaldehyde, or hardly any formaldehyde, higher in the atmosphere. Nitrogen dioxide, there is nitrogen dioxide higher in the atmosphere, and we use a model to estimate that and remove it. Ozone, we actually have sensitivity to the height. So ozone's a really interesting one. Tempo was designed in a really specific way to actually measure surface or near surface ozone. The other satellites have not really done this to the same sensitivity. And the reason is that Tempo is using ultraviolet ozone absorption, but it's also using visible ozone absorption. So if you have ultraviolet light coming in, the ozone in the ozone layer high up absorbs all of that. However, the visible light can get to the ground. And so if we combine visible measurements with ultraviolet, we can get an estimate of ozone near the ground and high up at the same time. And this it's very technical to really describe this in detail. It has to do with how far the photons penetrate on average at different wavelengths.
Okay. Well, thanks for your question, Bennett. All right. And I see one more. Hopefully I'm pronouncing your name right. Rao on YouTube wants to know about how about NH3 and CH4 monitoring?
Yeah, great question. So those are also monitored from space. We can't measure those. So these other instruments are measuring them though. So ammonia, excuse me, NH3 is regularly measured from an instrument called, a US instrument called CRIS. That's an acronym, of course, CRIS, and it's on a couple of NOAA satellites right now. And a European instrument called YASI, again, another acronym, and those are measuring in the infrared. So we can only, typically these instruments are designed to measure in different wavelengths of the spectrum, or different wavelengths of the electromagnetic spectrum. So we use ultraviolet and visible light, and UV and visible measurements are very well suited to measuring things at the surface. So they're very sensitive to surface pollutants. But again, like I was saying before, you can only measure molecules that are absorbing in UV and visible light if you're using a UV and visible instrument. So the instrument we have is designed to measure UV and visible. So we're measuring the suite of molecules that absorb there. But ammonia and methane, CH4, are both absorbing in the infrared. And so those are totally different instruments using different detectors and different optics, et cetera. So methane's a really interesting one. That's a very hot topic in satellite monitoring right now. So our group actually has an instrument called MethaneSat, and it's being led by the Environmental Defense Fund, the EDF. And it's a collaboration with the EDF and the Smithsonian and Harvard University and several other groups. And there's another, Tropomi actually measures methane. It has an infrared band. So it's measuring these pollutants like we do, but it also measures methane. And there's some Canadian small satellites called GHG-SAT, like greenhouse gas SAT, and they measure methane as well at ultra high resolution over facilities. So I'd encourage you, if you're interested in that, to go and look up some of those instruments. They're making really interesting measurements right now.
Yeah, and I think MethaneSat actually launches sometime this year, last I heard.
Yeah, I think it might be early 2024 now.
Oh, okay.
Yeah, but I'm not sure.
All right. Well, thank you, Rao, for your question. All right. Next question that I see, Carlos on YouTube wants to know, will I be able to download information for Mexico City?
Yeah, definitely. Mexico City is a big standout in pollution in our field of view. And so you should be able to go eventually to the NASA data archives and use what they call a subsetting tool, which will let you download just a segment of data. And there's definitely going to be a lot of interest in Mexico City. That we have some collaborators there who have a lot of ground-based instrumentation. So it's one of the main, what we call validation sites. So they have instruments at UNAM, at the university, and they have some up high, kind of out of the pollution layer on a mountain. And so we'll be using those instruments to check and make sure that the measurements from space make sense. Because when you put one of these instruments on a rocket and you launch it into space, and then you start analyzing the data, it's not always giving you what you think it's supposed to. We have to make sure that our analysis matches what we know is kind of the truth from the ground. And the Mexico City stations are going to be part of that. So yeah, and I think there may even be some plans for field aircraft campaigns over Mexico City. I'm not sure about that, but you'll be able to get that information, and definitely scientists will be looking closely at Mexico City. It's also where we have a couple of volcanoes in the field of view. So we also can measure sulfur dioxide. And there's not a lot of, thankfully, erupting volcanoes in the contiguous United States. So we don't see Alaska and Hawaii, but we do see the ones near Mexico City. So those are really interesting as well.
Yeah. Thanks for your question, Carlos. Okay. Looks like we have a question on Facebook. This time from Brian. Is it possible to measure pollutants in the oceans from things like oil spills?
Yeah, so that's a good question. I have looked before from satellite data to see if I could see like formaldehyde, for instance, from oil spills, and with the current instruments or the instruments I used in the past, I wasn't able to really kind of get the sensitivity for that. I think with Tempo, we'll be able to possibly see some of that if there is an oil spill. We'll probably be able to see the actual pollution that's produced just from oil drilling, though. So these platforms often produce like nitrogen dioxide or sulfur dioxide. And in the past, it's actually been kind of hard to measure it, but recent advances in instrumentation and higher resolution, that kind of thing, people are able to now look at pollution that's actually coming from like drilling platforms when there's not even an oil spill.
Okay. Thanks for your question, Brian. All right, I'm going to jump back to YouTube questions. This is an interesting one from Barbara. Does Tempo itself cause any pollution on any level? And then how long will it be observing?
Yeah, that's a great question. I guess in manufacturing anything, you're going to cause some pollution. And now I'm not an expert in this, but I know people who are. But of course, launching a rocket into space is not pollution free. So so launching rockets is definitely going to add something to the atmosphere. So yes, I guess there are trade-offs in this. So how long will it be observing? So the design lifetime and the funded lifetime for Tempo is 20 months. So just less than 2 years. But there's nothing about Tempo that is going to degrade necessarily. And so that's kind of like the first, this happens with a lot of space missions. Like they say, well, let's plan it for 2 years or something. But they can, as long as they're successful and the instrument's still working, it can be, renewed, every couple of years or something. What we probably will rely on is the spacecraft design life, which I believe is 10 to 15 years, probably 15 years. So when Intelsat decides that they need to shut down, then Tempo will have to go. And a lot of these big satellites, they are limited by, say, like propellant on board and fuel on board that they need to keep the orbit.
Right.
But yeah, there are plans NOAA has plans to have a continuity missions. So they have Tempo follow on in the hopefully in the works. So at some point, Tempo, if it's successful, will probably become like what we call operational. And that's when it becomes more like a weather satellite, not just a science experiment, but something that is integrated into the kind of like NOAA operational satellite system.
Okay, interesting. All right, thanks for your question, Barbara. Here's a bit of a technical question. We're interested in tracking cyanobacterial blooms. Can you look at chlorophyll on the surface?
Yeah, I don't know too much about this. I think you can. There are probably instruments that there are instruments that are better equipped for this, but with really high resolution measurements. There's one called Glimmer that I think will be launched in the near future as well for looking at like really high resolution surface ocean biology. But yeah, that's a good question. I'm not entirely sure how useful Tempo will be. It definitely will be, people are kind of like, it's not a primary product or anything, but looking at ocean color is an interest that some people have for looking at Tempo, but there are other instruments that might also be useful.
Okay. Thanks for your question. All right, so let's see. Mike on YouTube wants to know, does the Center for Astrophysics just collect data, or will it be used to propose needed changes to reduce the pollution?
Yeah, so that's a good question. So we basically, at the Center for Astrophysics anyway, we're kind of at the very beginning of the pipeline of this kind of data. So we are like taking the data, the raw data and detector counts, and turning it into a calibrated radiance value, and then deriving the gases from the satellite that the satellite measures, and then we provide that to NASA. And then NASA provides that data to anybody who wants it. So it will be, our job is really to kind of provide the best data possible. And then other people, scientists, will take that data to better understand atmospheric chemistry or better understand emissions. And then down the line, hopefully this data is going to be used by agencies like NOAA or Environmental Protection Agency to actually to better understand what's going on in the atmosphere, or in the case of the EPA, to actually use that data to I guess, whatever they need to do with it. So for regulatory work. But
Right.
Our job is really to just provide that data here.
Okay. Thanks for your question, Mike. Let's see. Looks like we have a question from someone at the CFA. So Jose wants to know, are there any TEMPO projects focused on monitoring the Amazon rainforest?
Yeah, great question. I wish there were. So TEMPO is sitting above the equator, and it's looking at North America. But it's looking at North America because we're measuring North America. We could, in theory, measure South America because we're at the equator. However, that would probably require us to have twice as much money. We'd need, more detectors, another telescope, et cetera, et cetera. So yeah, you'll note that the three instruments are all measuring in the Northern Hemisphere, and that's definitely a shame. But there's some scientists from various countries and industry are hoping or working to put geostationary instruments up that will also measure places in the Southern Hemisphere. But yeah, right now TEMPO is not able to do that. We regularly use low Earth orbit data, though, to look at the Amazon rainforest. So there's quite a lot of papers looking at all kinds of things to do with the Amazon and biomass burning and land use change from satellite remote sensing.
Okay. All right. Thanks for watching, Jose. Okay. You'll have to help me with this one, Caroline. So AC on YouTube wants to know, I think you mentioned breakdown of squalene generates formaldehyde.
I don't think I mentioned squalene specifically, but basically all volatile organic compounds, when they break down in the atmosphere, have formaldehyde somewhere along their chemical chain. And so we can't measure that directly. We can't measure most volatile organic compounds from TEMPO. We can really only measure two. The other one's glyoxal, and it's quite noisy. But formaldehyde is a really useful one because it helps us estimate other VOCs. And we can't get if there's thousands of VOCs, we can't infer back each one. But people will use models of atmospheric chemistry models to infer at least groups of VOCs. So, and if people, I didn't mention it before, but a VOC is there's many VOCs, like benzene is an example. But basically they're things that smell. So like paint and gasoline produce VOCs, permanent markers, and forests in the United States and elsewhere that smell strongly. They're all VOCs.
Yeah. Okay. I think I'm going to ask you one more question, and then we're going to close up.
Okay.
All right. So this one came in on Facebook. Has any TEMPO data been used to prosecute polluters? or I guess it could be, will any tempo data be used to prosecute polluters?
I don't think I can comment on that one. So,
Yeah.
So I actually don't really know about other satellite data. But it does help people to understand where pollution is coming from. And actually, a way that satellite data can be used is to, in a way, understand. People can use it to, states can use it to understand their own local pollution problems. So, and that's pretty important. Like, is our ozone really bad here, or is it ozone that's coming from somewhere else? And so it's important to, if it's coming from somewhere else, then you can I don't know, rest slightly easier in that you're not having a local problem that you need to deal with. But but I don't know. I would have to defer that one to the Environmental Protection Agency, I think.
All right. That's totally okay. All right. So thank you everyone for your questions. We got a lot of good ones, and we appreciate you tuning in to Virtual Observatory Night. And thank you again, Caroline, for joining us. So this concludes Observatory Night. I look forward to seeing you all again for the next Observatory Night, which will be announced at a later date on our social media channels. In the meantime, visit our website, cfa.harvard.edu, to learn more about TEMPO and the Center for Astrophysics. Thank you, everyone, and good night.